topic, which is nothing but the impedance matching methods. So, there are different methods that we generally use to match the impedance. So, before getting into this topic, first let us discuss about what is mean by impedance matching. Okay. Suppose just consider that you're having a transmitter and you're also having an antenna which is going to receive the information that you're going to transmit. Okay. So, just like that, you couldn't actually transmit an information from the transmitter to the antenna, right? In between the transmitter and the antenna, we generally need a matching network in order to match the impedance between the transmitter and the antenna. Just suppose, let us assume that the transmitter has an output impedance which is 150 plus 75 j ohm. Okay, and the antenna has an input impedance of 75 plus j 15 ohm. So we know that both of these impedances are not equal. Okay, since both of these impedances are not equal, some of the power from the transmitted will be reflected back instead of going into the antenna. This is where the matching network actually comes into picture. Okay, so whenever I want to match the impedance between the transmitter and the antenna, I'll be using a matching network. So in the matching network, we generally have two different components. So one is going to be your capacitor and another one is the inductor. So I'm going to place the capacitor and inductor between the transmitter and the antenna for the purpose of impedance matching. Okay, so the purpose of this inductor and capacitor is to make the antenna look like a correct impedance to the transmitter and make the transmitter look at the antenna as the correct impedance. So this is what actually we mean as impedance matching. Okay, so why do we actually concern more about impedance matching is that in order to have a maximum power transfer between the transmitter and the receiver. Whenever I want the maximum power transfer, which is the source impedance, we just define it as Z source, should be equal to the load impedance. So, Z star of load, which is nothing but the complex conjugate of the load impedance. Okay. So, as I have stated earlier, if the transmitter impedance is ZT, that is equal to, let us assume that it is going to be 150 plus j 75 ohm. Therefore, that the impedance matching network should be present to the transmitter is the conjugate of the antenna's impedance. Okay, so if the antenna's impedance is 75 plus j 15, the impedance which should be available at the transmitter side should be equal to 75 minus j15, which is nothing but the conjugated version of the load impedance. So that is going to be my target, right? So in simple words, we can say that uh, you look like I look like 75 plus j15 ohm. The matching network will transform the impedance to 75 minus j15 ohm. Only then the maximum power will be transferred. Okay. So next we have to discuss why do we actually use a capacitor and inductor, and we generally call it as L section. Okay, so you can look at this images, which is 8 possible configurations of discrete two component matching network. It contains only two resistive component, which is going to be your capacitor and inductor. Okay, they are arranged approximately like the letter L. So that is the reason we call it as L section matching. So we have several possible arrangements of these two components. Okay, so the important idea between this is we choose the appropriate arrangement of one series component and one shunt component to transform one impedance into another. That is the main reason behind it. Okay, and what are generally what is mean by or what a series and shunt component is, actually this is very important. So series component is nothing but a component which is placed in the signal path is generally what we call it as the series component. So for an inductor, the impedance ZL will be equal to J into X in XL. So where XL will be equal to omega L, okay? And shunt component is nothing but a component which is actually connected across the transmission line is called as the shunt component. For the capacitor, its admittance is denoted as YC, that is equal to J into BC, where BC will be equal to omega C, and we all know that omega is equal to 2 pi f. Okay, so in this example which we have discussed, we have discussed about a capacitor which is in shunt and inductor it is in series. Okay, um, so we can also discuss this approach with an example as well. Okay, this is going to be the analytical approach. So in this example, they have defined that the frequency is going to be nothing but 2 gigahertz, and the transmitter impedance is 150 plus j 75 omega, and antenna impedance is 75 plus j 15 omega, and our target is to find the value of the capacitor and inductor so that the transmitter and the antenna is properly matched. Okay, so we are going to use the formulas. So the impedance ZM can be computed as a series connection of the inductor and a parallel connection of C and ZT. So by using the formula, I can define ZM, that is equal to 1 divided by ZT inverse plus J into BC. The reason is I'm going to connect ZM in the series combination of inductor and parallel combination of the capacitor, plus J into XL will give me the actual impedance which I have to see at the which is nothing but the receiving antenna side. Okay, so the step one is nothing but the transmitter is impedance ZT is combined with the shunt capacitor. The resulting impedance is then combined with the series inductor. So finally, we'll be able to obtain the impedance which should be ZM, that is equal to ZA star, or I can also define it as ZM should be equal to, which is nothing but the conjugated version of the load, which is nothing but 75 minus j into 15 omega. So actually, what are BC and XL is nothing but this is just a convenient way for representing the capacitor and inductor. So for capacitor, BC will be equal to omega C, and for an inductor, XL will be equal to omega L. So instead of just directly solving C and L, we have defined here as BC and XL, and this will get converted into C and L. Okay, so by solving all these relevant equations, we can obtain that the value of BC will be equal to 9.2 milliseconds, and XL will be equal to 76 ohm. So in order to find the value of the capacitor BC, which is equal to omega C, so I have to find the value of C, so I'm just going to divide it by omega. So 9.2 milliseconds divided by 2 pi into F, which will give me 0.73 picofarad. And similarly, we have to find the value of inductor L. So we know that XL is equal to omega L. So L, that is equal to XL divided by omega. So we have obtained the value XL is equal to 76 ohm, and dividing it by omega will approximately give us the value of 6.1 nanohenry. Okay. So what you're going to do is just you're going to go with an L section in which you're going to connect the inductor in series and capacitor in shunt. For the frequency of 2 gigahertz, the value of the capacitor should be equal to 0.73 picofarad, which is in shunt, and inductor 6.1 nanohenry, which is going to be in the series format. So I hope you have got an idea of how we are going to do the impedance matching just by using the passive components, and which is nothing but the inductor and capacitor, which is going to be your L section, and many possible combinations are available. You have to just find the value of L and C. So in the upcoming videos, we can also discuss it with the approach of Smith chart as well. Thank you.